Good morning. Today is our last section in Chapter 1, and tomorrow you'll have the whole day to do the review. My binder will be up in the front, the iPad. I'm not going to be here tomorrow. I'm going to a funeral. For any of you who know Champ Nelson, his father passed away, so that's where I'll be. Today we have a few vocabulary things and a couple of examples. And it's the last day where we talk about this recursion thing where we use the UN and the UN sub 1. And we're going to include things that are what we call non-linear. So that's going to be something that's kind of important to note as we go along. So a linear graph is one where all the points bless you, lie on a line. And there is a constant rate of change and the sequence is arithmetic. So you might recall that we did something like this where we said something like UN equals UN minus 1 plus 5 as an example. So all points lie on a line. There's a constant rate of change. That means like you're going up by 4 each time or down by 3 each time. And that's called arithmetic, which we've already talked about. A curved graph, on the other hand, means that we have a non-constant rate of change. In the past, this has been a geometric sequence. And an example might be something like UN equals UN minus 1 times 1 minus 0.25. And then the last part in here, this thing that says discrete graphs. These are graphs made up of non-connected points. So kind of like you might remember that in our calculator we have this thing called a scatter plot. Something like that. That's what a discrete graph is. Something like a scatter plot. So maybe an example is a scatter plot. That's our vocabulary for the day. Questions about any of those 3 vocabulary phrases? All right. Down below here, we have some tables and some graphs and some equations. And what we want to do is we kind of want to match up the 3 parts together. So you can understand what would the table look like, what would the recursive equation look like, and then what would it produce as a graph if I was graphing it. So I'm going to try and scroll down here all the way so you can see all of these at the same time. and it's basically just a matching game. So I'm going to try to color code things so you can kind of see what's going on. I guess one of the things I like to look at is I'm a picture person. So I'm going to try and look at pictures to see what works out picture-wise. So like for example, in number 1, I notice that there are dots straight across. Or in other words, that every single y value is -4. So I look for a table that has all the y values at -4. So I see that this number 1 right here is the same as, looks like to me, number 6. And then really all I've got to do is I've got to find something that tells me I stay the same all the time. So when I look at A through F and I see each of these equations, my starting value, what's my starting value? -4. So I look for a starting value of -4, and there's only one of them. So that's this one. So I know those 3 pieces go together. That makes sense? Table, equation, graph. I would like you to ignore where it says the where n greater than 1. That just means that if you start at 0, your beginning value, then from then on keep going up. So the next one's the first one, then the second one, then the third one. That's what the n greater than or equal to 1 means. So you don't really have to worry about that. That's not a major concern for us. We don't have to worry about that in our calculator or anything like that. I want you to take the next 5 minutes and try to match up the rest of these graphs, and then compare them with a couple people around you. So let's take a look at some of the other strategies. So this is how my brain works when I'm thinking about stuff. Might not be the same for you, but this is how I think about it. If I look at the second picture, what I notice about the second picture is it's one of only 2 graphs going down. So II goes down, and so does IV, or number 2 and number 4. These are only 2. So if I look at a table where things are going down, number 1 goes down, and number 5 goes down. So if I try to match up the picture of number 2 here, going down, I notice that it goes from 1, 6, it looks like, to 2, 4. But I don't see a 2, 4 in table 5. But I do see that in between 1 and 3 would be the 2, and in between 6 and 2 would be a 4. So I'm pretty sure that table number 5 goes along with picture number 2. Notice how they didn't go 1, 2, 3, 4. They jumped around. And that means that the only other one that goes down, which is IV down here, Roman numeral 4, has to be the only other table that goes down, which is table number 1. So now I got to match those tables and pictures to their equation. And what I notice is that picture number II is going down at a constant rate, or in other words, it's linear. So if you're going down, back from our recursive equations, that means that I'm going down by the same amount. In other words, subtracting off something. So when I'm subtracting off something, I look for an equation where I start somewhere and then I subtract off a number. There's only one that subtracts off a number, it looks like, and that's D. Looks like.
A.
Oh, I mean A, sorry. Thank you. So A is the equation that matches up with the picture and the table. So then in orange, since I'm not subtracting but I'm going down, that must mean that I'm multiplying by a number less than 1 to go down. So now I look for something in picture IV where there's an equation where I'm multiplying by a number less than 1. So here I'm not multiplying by a number, here I'm multiplying by a number more than 1. So it has to be F or B. And so if I look at those two, this one is what they call a shifted geometric. And remember, there's only one that's going down, so when you shift geometric, that's when we had an end value, like a limit as you go, and it kind of levels off in the end. So it can't be F, which means the only one left over is B. And then the next thing that draws my eye out of the pictures, that is, because I like to start with the pictures, is V, which is number 5 in Roman numerals from the graphs. And if I look at that one, I see that I'm going up at a constant rate, which means I'm just adding something. So if I'm just adding something, and I look at where I might just be adding something, as I look at V, I look for one of the equations where I add a number on. So there's F, where I'm adding 2, and there's D, where I'm adding 2. But F has something multiplied by it in addition to the adding, so I don't like that one. So I'm going to choose D. And then I look for a table where that might happen. Please wait to sharpen your pencil since I'm in the middle of teaching. Thank you. So now I go in the table and I look to where I'm adding the same kind of number, or at least the dots match up. So it looks like the far right dot is 6, 10 maybe, or something like that. And so I'm looking for that one somewhere. I don't know if I see that anywhere. Maybe 4. Does 4 look like it could be right? There's no 6, but in between 8 and 12 could be 10. If you're going up by the same rate. So I think that table matches up with the V. And now I only have 2 things left. And both of them are going up. And both of them look like they're starting somewhere around 0, but I'm not sure. And what I notice is that ii in the graphs, if I'm looking at that one, levels off in the end. And yesterday we just got done talking about a shifted geometric where we had what they called a limit. That's a y value where you can't go past it. You get really close to it, but you never reach. So I'm looking for an equation that's a shifted geometric. Or in other words, I'm multiplying by number and then adding something in. The restock value. So out of the 2, the only one that has a restock is F. And then I'm also looking for one that looks like it's leveling off. And to me that looks like it's table number 3 that I'm leveling off with. And then by a process of elimination, of course, that means that the only one that's remaining has to be number 2, letter C, and graph VI, or in other words, Roman numeral 6. So that's how my brain works as I'm doing these. I like to start with the pictures. You don't have to. There are lots of different strategies. You can use any one of those. So let's work backwards. Let's look at number 3 first. In number 3, they talk about the air temperature, and as it gets warmer, crickets chirp faster. And you can use a snowy tree cricket's rate of chirping per minute to actually figure out the approximate temperature. So in this table, we have the temperature in degrees Fahrenheit. Notice that it jumps by 5 degrees each time. And then we have the number of chirps. So as we look at this table, something that's really important, because when we work with the equations, usually we go up by 1 each time for the independent value, like the x value. So these are like the x's. These are like the y's, or the independent and the dependent variables. And I notice that every single time that I go by chirps, I'm adding 5. Every single time. And every single time that I'm looking at the temperature is actually going up by 20. Oh, every time I look at the temperature, I'm going up by 5, and the chirps are going up by 20? Did I say it backwards? Yeah. I'm sorry. So my rate, the chirps go up 20 for every single time my temperature goes up 5. So my amount that I'm going up by each time is not 20, because that's for every 5 degrees that I change. So if I want to find my actual rate, the way that I would calculate that is my rate is that I am 20 chirps for every 5 degrees Fahrenheit. And in math,